For my fifth and final laboratory experiment, I analyzed the motion of a volleyball I threw up and hit. In doing so, I was able to discover how much work I imparted on the ball in the action, and I was able to demonstrate the energy principle at work in the real world. To track the motion of the volleyball, I used the software tracker. I had my roommate film me as I hit the volleyball, and I used the point mass feature to track the ball through each frame. I used my height of 6 feet, or 1.829 meters, to calibrate the axes. Through applying various physics principles, namely the energy principle and Newton's second law to a lesser extent, I was able to create the following computational model that mimicked the ball's motion. Above are some helpful formulas that were used in the analysis and in my generation of my code. The first is the guiding idea behind our experiment, the energy principle, also known as the work-energy theorem. It states that the change in total energy of a system is equal to the work imparted on it from surrounding sources. In other words, a system cannot gain total energy without being influenced from the outside. The following two formulas are those of the kinetic and gravitational potential energy, respectively. Both of these make up the total energy of the system, as our system of choice consists of the ball and the Earth. Without the Earth in the system, the ball would not have gravitational potential energy. Since we're performing the experiment close to Earth's surface, the formula mgh can be used to represent the gravitational potential energy. The final two formulas used in the experiment represent Newton's second law in the form of the position and velocity update formulas. Such formulas are what actually display the movement of the ball in the computational model, as they are applied in every iteration of my code. So why is this all so important? Why does it matter that we can show the energy principle at work? The energy principle is perhaps one of the most important concepts in all of physics, as it is omnipresent among us. Through it, we can display how the total energy of the universe is constant, and that energy cannot be created or destroyed. To create the model, I used the starter code from Lab 4 and made several major alterations. I first specified the volleyball's mass of 0.27 kilograms. To find the initial position of the ball, I used the first output in tracker from the observation. To compute the initial velocity, I used the slope formula for both the x and y components with respect to the change in time for the first two position outputs in tracker. I then specified the formulas for the kinetic and gravitational potential energies observed. These formulas are merely translations of those specified earlier in the video. Next begins the first while loop of my code, which represents the period of time from which the ball was released from my hand to just before I made contact in a hitting motion. Since the only force on the ball in this period is the force of gravity, I assigned the variable fnet to simply mg in the negative y direction. This is critical in calling the velocity update formula, which I listed in the next line. Upon calculating the new velocity in the iteration, I can then update the ball's position. To calculate the change in the ball's energies, I subtracted each energy, kinetic, gravitational, potential, and then the total, which is the sum of the two, from the previous iteration from its counterparts in the current iteration. This while loop ends as soon as I hit the ball at time t equals 0.567 seconds. Before launching into the next while loop to display the ball's motion after the hit, I specified the ball's velocity during the hitting motion itself at time t equals 0.567 seconds. At this point, there's work being done on the system, changing the total energy. After this instant, however, the system returns to its previous state in which no work is done and no change in total energy is made. Thus, the second while loop performs the exact same function as the first, except with a new initial velocity. Running my code yields the following results. The ball travels upward and slightly backward before coming down for the hit. After this point, the ball follows an arc-like motion until the end of the simulation. The change in energy versus time graph displays the results that are consistent with major physics principles. At all points except for that in which the ball was being hit, the change in total energy, represented by the orange line, was 0 joules. This makes sense, as no external entity imparted work on the system at these points. The sudden spike in total energy change represents the time at which I hit the ball. The gravitational potential energy remained relatively stable at this time, since it's only contingent on mass and height and the gravitational constant g, but the sudden increase in velocity influenced the kinetic energy of the ball. Looking at the individual energies as functions of time, it makes sense that the gravitational potential energy curve closely resembles that of the y position versus time graph, as the height of the ball above the ground is the only changing factor in the equation. The kinetic energy versus time graph displays the two major loops as concave up parabolas, linked by a sharp increase to represent the hitting motion. The relative minima in the two parabolas correlate with relative maxima in the potential energy versus time graph. So how much work did I impart on the system? By the energy principle, the magnitude of the spike in total energy represents the work that I put into the system. Ultimately, I added 7.28 joules of work in the hit. What could I have done better? To perhaps improve on my experiment in the future, I can make the distinction between rotational and translational kinetic energy as the ball flew along its trajectory. I could also have utilized a component for air resistance in my computational model, though this would ultimately show a net loss of total energy to thermal energy.